Good evening, sir. Povitra, sir.
Good evening. Good evening. Am I listen? Am I audible?
Sir?
Just a
Povitra,
minute.
sir?
I connect my headphone. Just a minute.
Yeah. I can hear you now.
Okay.
How are you, sir? Sir? Povitra, sir?
Am I audible?
Yes. You are audible, sir.
My voice is clear, right?
Yeah. How are
Okay.
you, sir?
I'm fine.
It's
Just
been a
give
long time
me.
talking to you.
Oh, no, it's okay.
Oh.
Take.
We are waiting for some more participants to join.
Okay.
We shall be started nearly around 7, 6.
No problem. No problem. I'm here.
Okay, sir. Sir, we are starting the session, sir. Pavitra, sir?
Hi, yes. Am I audible?
Yeah,
Hello?
yeah.
Okay.
You're audible, sir.
Your name is Suruji.
No, sir, I'm Ritinavo.
Oh, Ritinavo. Sorry.
It's okay,
Okay,
sir.
okay, okay. I think Dr. Hussain has joined, right? No.
Yes, sir.
Okay.
So, I welcome you all in the AICTE ATAL FDP program. This is the fifth evening. Sorry, this is the fourth evening we are having right now. And for this evening, speaker is Professor Povitra Kumar Pal. Professor Pal at present working as a professor at physics department of sorry at Department of Physics, Jadavpur University, Kolkata. He is doing research in organized thin films such as Lemur project, layer by layer self-assembly, biosensor, organic electronic devices, metal nanoparticles, etc. He has published various interesting research papers in reputed international journals from ACS, RSC, Elsevier, Springer, IOP, Taylor and Francis, etc. He did postdoctoral research as a Raman postdoctoral fellow at the University of Texas at El Paso, USA. He visited Osaka University, Japan as a visiting scientist. He already awarded 3 research students, one submitted for PhD, and many PhD students are still working under him. He worked as principal investigator of various research projects funded by DST SAR, West Bengal DST, UGC, RUSA scheme, etc. So with this note, I welcome you, Professor Pal. Please present your lecture, sir.
Thank you. Just a minute. Is it visible?
Yes, sir. It's visible.
Okay. Thank you, Professor Hussain, for inviting me in this AICTE sponsored FDP program at Tripura University. And I also thank to all the faculty members to Tripura Department of Physics, Tripura University, and also the other all the participants here. Okay, so in this evening, my talk is basically on a topic which is the fluorescence spectroscopic and electrical characterizations of organized molecular assemblies on solid substrate. So the name title is very you are very familiar, that is fluorescence spectroscopy, organized molecular assemblies, that is thin films. Okay, so in this lecture, I have two parts. Part A, mostly on the optical, the fluorescence properties of the organized molecular assemblies, and also some very basic concepts of the fluorescence relevant to the research. And the second part B, will be on the electrical characterizations of some organic molecules, and also some basic aspects of the electronic structures relevant to the electrical characterizations of the organized molecular assemblies. So, so in the introduction, I must say that this the organized molecular assemblies of various organic inorganic hybrids, the biological compounds in the restricted geometries have received significant attention due to their promising applications in number of technological fields. And among these various organized assemblies, Langmuir-Blodgett and layer by layer self-assembled molecular architectures are very significant, very important in the field of modern science and technology. And many of you are aware of the Langmuir-Blodgett technique, and which is an elegant approach for creating the ultra structure or the supramolecular structures with a very precise control over the molecular architectures at a nanometer level, and it is very easy to manipulate or modulate their physical and physicochemical properties, which are very different than their bulk, crystalline, and solution phase. So one can have this unique and precise control over the arrangement of the molecular dipoles, what I can say the molecular dipoles, okay, chat or error interface, and that unique structure of the molecules can be easily transferred onto the solid substrate, okay, for further characterizations and for the application purposes. And to characterize those interesting supramolecular or the ultra structures fabricated by the Langmuir-Blodgett technique, various analytical approaches have already been attempted by various scientists, and for the organization and physical properties of such organized thin molecular films onto solid substrate. So among the various techniques, fluorescence emission spectroscopic method is very popular to know the molecular mechanism involved in the excited level of the organized molecular assemblies. So, and these properties have already been significant attention to explore the molecular level sensing approaches, even in the molecular electronic devices, such as to study the aggregation of the molecules for the different electronic and optical properties, and also to understand the biological properties or the molecules in the biological environment, okay. So the fluorescence emission measurements, measurement analytical approach is a very excellent technique, and it is widely used in industry as well as in the research, okay, both in academic and practical purposes. So on the other hand, the electrical characterizations, namely the current voltage characteristics, is also very popular to characterize the organized LV film, and this type of characterizations have already gained considerable interest in designing various molecular electronic devices because of unique structural conformations of the molecular species in the organized in LV films, so which are not present, as I said earlier, not present in the bulk crystalline form. And the various literature reveals basically that fabrication of organic diodes, thin film transistor, organic light emitting diodes, sensor, etc., can be designed from the ultra thin organization of various interesting conjugated organic materials assembled in Langmuir-Blodgett films. So already in the literature there are many publications regarding this, but still it is in the early stage of research. And for the next generation electronics, the molecular electronics, the scientists are basically focused or have given much attention in this important area, because already in the market the organic light emitting diode, organic displays, organic thin film transistor, but still their the retention capacity, their sustainability, their the cost of manufacturing, all these are not yet still optimized. So this will and also there are a wide variety of organic molecules, but the scientists are basically trying to find out the optimum structures for the low cost manufacturing of the electronic devices in these important areas, okay. So the research is very important in this the organized thin film and their spectroscopic and electrical characterizations. So in the modern nanoscience and technology, modern molecular electronics technology, and so on. and the flexible in the modern day technology, there is a flexible electronic technology. So organic molecules have much more potential to design the flexible electronic devices. Okay, so to cater all these objective, the interesting applications, we have to deal with this fluorescence electrical characterizations in much more detail, much more, we need to manipulate the structures, and there we need to extract interesting physical and physical chemical informations which are especially important to achieve this important goal. Okay, so as my talk is on the fluorescence spectroscopy, first of all I try to just give you some overview of the electronic spectroscopy, mainly the fluorescence spectroscopy. And the fluorescence spectroscopy basically belongs to the central part of the electronic spectroscopy of the molecular physics. And in this context, I must say that we know the atomic physics, we know the molecular physics. So why should you consider about the molecule? Okay, what is the difference between the atoms and the molecules, and why the molecular spectroscopy and why the electronic spectroscopy? So these questions are very important and very pertinent in this present discussion. So, and in case of the molecules, how do you define the electronically excited state for the molecule? Okay, so in case of the if you go back to the atomic physics, the atoms, okay, we have defined different atomic orbitals like s, p, d, f, etc. And also you have defined many quantum numbers like n, l, m, s. Okay, and also the angular momentum in quantum using with the help of the quantum mechanics. But
Excuse me,
yes,
Professor Pal.
yes.
Okay, I think your slide is not moving. Now I see what is an electronically excited state. So are you showing this one?
Oh, yeah. What is electronically excited state? Is it visible?
Yeah. Oh, okay. So you are discussing same slides?
Yeah, same slide. I'm just giving some introduction.
Okay. Then.
Okay.
Thank you. Sorry.
Okay, it's okay, no problem. So, so in the introduction, these are the questions actually before going to the electronically excited state for the molecule. So, my dear colleagues, my dear students, and all we should understand this important aspect. Okay, so the molecule basically they are formed when the atomic orbitals are overlap, okay, to each other, and the electronic behavior of the atom basically changes in the molecule because of the overlapping of the atomic orbitals, and that atomic orbitals basically overlap with the linear combinations of the this atomic orbital, and they form the molecular orbitals. Okay, so that means we don't have the in case of this inorganic system like atoms, when you will talk about the atoms, you will have the discrete energy levels, but the electrons are the localized, okay, the wave function. So here basically in case of molecule, these are the electronic wave function, the electron orbitals are delocalized here, okay, to have the stable structure or to maintain the resonance structure of the molecule. Okay, so these are very preliminary thing. Many of you are aware of this, the formation of the molecule, okay, and the resonance, the molecular orbital. Okay, so we are now talking about the electrons which are in the molecular orbitals. Okay, so generally the luminescence, the fluorescence is a kind of luminescence, and the time scale in the nanosecond time scale it belongs. So and it is a photophysical process, and most of the organic molecules, aromatic organic molecules, we can have this type of process giving the luminescence. So atoms of different elements have different number of electrons distributed in several shells. As I already told you, the atoms, different elements have different number of electrons distributed in different shells, and the electronic transitions are basically responsible whenever you talk about the luminescence, okay, so the electronic transitions are responsible for that type of luminescence. Okay, so on absorption of light, when the light is falling on the molecule, the molecules electrons in the molecular orbital can go to the higher molecular orbital, okay, or higher energy state, okay. So the on absorption light, electrons are excited and are lead to the high energy state, okay. So before excitation in the ground state, some of the electrons are in the so-called HOMO state, and which is called the highest occupied molecular orbital. When the two atomic orbital combine, so there are two molecular orbitals, one is HOMO and another is LUMO, okay, depending upon the and the extent of the HOMO and LUMO, it should be the extent of overlap, okay. Then the overlapping, if you can recall the orbital overlapping, so there are in phase and out of phase overlapping, we know, okay. So the electrons, the two atomic orbitals, they are split into two energy levels. The highest energy levels is called HOMO and the lowest is called a LUMO. That is, HOMO is the highest occupied molecular orbital, and but in real practice, what happened? Real polyatomic hydrocarbons or polyatomic aromatic molecules, this lot of energy states you can have the HOMO -1, HOMO -2, and LUMO +1, LUMO +2. But LUMO is the lowest and HOMO is the highest occupied molecular orbital. So in normally, HOMO is most stable, actually entropically favorable, most stable energy state of the molecular orbital. So when excitation occurs, the electrons go from HOMO to the LUMO level, okay, after excitation. So after they reach the excited state, they are in the LUMO, or the lowest occupied molecular orbital. And you can see this picture, this right hand side, this picture, the energy scale low to high, and this is the HOMO, and the electron spinors are paired here, up spin and down spin, and you can see here that electrons gets excited and go to the LUMO level. So this is the excitation of this is the process of excitation from the molecular orbital of the organic molecules, okay. So, and the excitation, there is a time scale also 10 to the -13 second, something like that, okay, or 13 to 15 second, okay. So, and after excitation, there are various phenomena can happen in the excited state of the molecule, okay. So when the electron excited in the excited state, now the question is how the electrons can deactivate and returns to the electron's energy is deactivated, and the electron can return to the ground state. So this is called the deactivation of the electronically excited states. So the electronically excited states are basically unstable. So it is not favorable normally, okay. So the electrons have to relax to the lower energy states, okay. By several phenomena. I come to the point, the discussion. So during the return to the ground state, the excitation energy is released again. So the energy which is absorbed by the electron to reach the higher energy state, it will be released by and finally return to the ground state, okay. So both, and during this process, both the radiative and non-radiative decay process may happen, okay. So not all the energies which was absorbed by the molecule will be emitted, okay. So there will be some loss of energy as absorbed by the molecule. So most of the time decay is non-radiative. For example, it can be through the vibration or relaxation, because the molecular energy states molecular electronic energy states we can classify in different way. That is the electronic states, electronic energy, the vibration energy, and the rotational energy. Because molecules are formed because of the two nuclei or more nuclei come closer, okay. So vibrational degrees of freedom plays an important role for while defining the overall energy of the molecule and also the rotational energy. But in general, if you talk about the UV visible absorption spectroscopy, that in that range, actually the normally electronic energy is much higher compared to the rotational and the vibration energy. So the scale is electronic energy is higher than the vibration energy and then the rotational energy. So so the vibrational degrees of freedom is important, while the electron, you see it in this picture here, the deactivation pathways, the radiative and non-radiative. So radiative is fluorescence, phosphorescence, and non-radiative is the internal conversion and intersystem crossing. You see in this picture, this is the ground state of the electron, and this is the excited state of the electron. Is it visible, the slide, Professor Hussain? Hello?
Yes, yes,
Okay, okay. If you is not visible, please tell me, okay?
yes.
Okay. So ground state, this is all, these are ground vibrational state you see, and this is the upper state and upper vibrational states. Okay. So normally when electron absorbs energy or molecule absorbs energy, the electrons go to the upper vibrational state. Not only the S1 but S0, S1, S2, Sn. So many vibration levels electron can reach. Okay. So when electron go to the upper vibrational level, normally electron.
Excuse me, sir.
Yes.
Sir, cursor is not moving, I think.
My mouse cursor.
Yeah, sir, the pointer is not moving.
Is it okay now? Is it moving?
I am not seeing.
Why?
Just try to move forward your slide,
Yes.
because still it is in the same slide. What is an electronically excited state?
Why? Just a minute. Okay, I share once again. Just a minute.
Now it has came. Now it has came.
Oh, I see. But I need to full screen, nah? Otherwise it will be difficult to visualize.
Yeah.
So when I do full screen, okay, I scroll. Is it okay? Scrolling there?
Now you are in second slide, I think.
Yeah, it's deactivation pathways.
Oh, it's okay. Now it is.
No, it's the same.
Just a minute. I need to change the connection to other connection.
ওষুধটা নিয়ে এসে।
Hello.
ওষুধটা নিয়ে এসে। ওষুধটা নিয়ে ঢুকে। হ্যাঁ? আরে এই তো।
Hello, Professor Pal. Hello. Hello. Professor Pal, can you hear us?
Is it okay?
Yeah. So again, you please share your slide.
Sure. I changed the internet connection actually. Sorry. Okay. Is it okay?
Yes.
Okay.
So you please make it full screen and try just moving.
Okay.
Whether it is
Okay.
moving or not.
Okay. I'm moving. Okay. Is it okay? What is the electronic excited state?
No, now we see deactivation pathways.
Okay. Now. Okay. Now.
Same. So without full screen, you try to move.
This is university connection. I don't understand why it is happening.
Oh, yeah, now it's okay. I think in this way you can continue. This is visible.
But
So you please
but
continue.
it'll be difficult to visualize, right?
No, it's okay. We can see. You can read. No problem.
Okay.
Please.
Is it okay now? Scrolling now?
Yeah,
Scrolling
this
over
is-
there.
Yeah.
Okay.
Please continue.
Okay, thank you. Okay. We were actually doing the discussion about the ground state and the excited state, the vibrational relaxation. So the electrons absorbs energy and to the higher vibrational level. Okay. So after getting the excitation, the electrons will go to the ground state, but there are several things happen. One is the vibrational relaxation. The electron from the upper vibrational level of the of the excited state is Sn to return to the S1 of the zero vibration level of the S1 first excited state. Okay, and then electron relax to the finally go to the ground state. Okay, any vibrational level of the ground state. Okay, so this is this vertical transition is basically governed by the Cash's rule, and this this due to the vibration relaxation, this loss actually is the non-radiative loss. So definitely the absorption and the emission spectra do not overlap actually. So absorption emission will be always on the longer wavelength or lower energy side. Okay, so you see in the picture there is internal conversion, and this is the triplet state. Okay, triplet state is the the spin parallel, and all this one, these are the singlet state, and S0 is also the singlet ground state because of the alternate spin, up and down spin. Okay, so normally most of the molecule going to the triplet state is not favorable because the spin has to flip over there. So most of the aromatic hydrocarbons, you see this type of S1 to S0 transition, unless some special conditions are there. Okay, so that is triplet to singlet transition is called the fluorescence, phosphorescence. We are not discussing on the phosphorescence. So this is the this is called the radiative transition, is the fluorescence, and the time required to finally relax to the ground state or ground vibrational level is about a certain nanosecond, about 10 to the power or order of 10 to the minus 9 second. Okay, so and depending upon and the value of this I mean the time is depends upon the different the nature of the organic materials. Okay, so this is a very basic concept of the electronic transitions and the absorption and emission of the emission, especially the fluorescence I'm talking about. So so this I've already told you, this is the time scale for the fluorescent to -9 to -5, this order. And one important thing while designing various molecular electronic devices, optoelectronic devices, sensors, this is the Stokes shift. Stokes shift is basically the emission, the difference of the emission peak and the fluorescence excitation peak. Okay, so normally there are some difference between the emission and absorption excitation peak, and this is the and lifetime fluorescence lifetime is also correlated with this Stokes shift. Okay, so the excited state dynamics is highly correlated with this Stokes shift. So this is the schematic representation of the principle of the fluorescence. Many of you are familiar with this very basic concept of the fluorescence. So so normally the emission is occurred due to the transition from zero vibration level of S1, that is first excited singlet state, to the zero or higher vibration level of the ground electronic states. So normally that is why the electronic spectroscopy, you see most of the spectra are a little bit broadened, not too much sharp like IR spectrum. Okay, so it's a little bit broadened all the time. Okay, so especially the absorption spectroscopy, we see this type of broadening much more prominent. Okay, because of we cannot decouple the rotational and the vibrational degrees of freedom of vibrational transition. So this is the emission, fluorescence emission, the mechanism of the transition responsible for the fluorescence emission. Okay, so this the manifestation of these transitions involving the different states will depend upon the different I mean electronic nature or electronic structure, and that is also depend upon the several factors like the microenvironment, any other neighboring molecule, intermolecular interactions or intramolecular interactions, okay, the temperature, etc., or even sometimes the light can induce some type of changes in the electronic structure, okay. So this is the very basic what I have mentioned, okay. Now I come to the another important aspects, that is what phenomena basically we have normally we see while while talking about while doing research in the organized films or in any condensed media, so medium for the organic molecules. So molecular aggregates are very common, which you frequently encounter. We are in with these the molecular aggregates, okay. That is basically it is due to the intermolecular interactions when the molecules are come closer to each other, okay. So both in a ground state and in excited states, the interaction may happen, and due to the interaction, their transition dipole moment can interact, and finally, due to the interactions with the transition dipole moment, there is a splitting of the excitonic levels, and which are basically manifested both in the absorption and the emission spectra, okay. So normally there are two type of I mean the aggregates are normally I mean we observe one is the H type aggregates, another is the J type aggregates, okay, because depending upon the orientation of the both the stacking of the molecules and the orientation and the angle between the transition dipole moments of the two monomers, okay. So and also similar to the absorption spectrum, you see is it visible the excitonic splitting picture, the H and J aggregate very small, okay. So in the picture I just tell you that left hand is the H aggregate, is called the parallel stacking, and the middle is the monomer, and this is the ground state and the monomeric state, and the right hand side is this the these are the end-to-end stacking, which is called the J stacking, okay, J type aggregates. So depending upon the interaction type and the angle between the monomers, different type of aggregates are observed in case of the organic molecules, and both these type of molecular complexes are can be observed with the help of the both absorption and the fluorescence spectroscopy, but their signatures are different for in both in absorption and emission spectroscopy. So this is the H and J dimer J aggregates, and when dimer means when you talk about two molecules molecules come closer, it's called dimers. When more and more molecules come closer, and then they can create a they can form the cluster aggregates, okay. Then we call it the aggregates, J and H type aggregates. Another observation you can have in your research when you do the research with organic molecules, that is the excited state dimer, that is called X-imer, okay. So there are several molecules which do not interact significantly in their ground state. However, the many molecules, they do not interact significantly in the ground state, but when they are in the excited state, they basically reasonably form the stable complexes in the excited state, and these complexes are basically known as the X-imers, okay. And these X-imers are only existed in the excited states. When they return after the relaxation, when they return to the ground state, they vanish, okay. That means the existence only in the excited states. So that is why it is called the excited state dimer or X-imer, okay. And X-imer also generally we observe in the longer wavelength side of the emission spectrum, and the band is generally the structureless band is observed in the longer wavelength of the fluorescence spectrum. So, and it is also very important to know what is the origin of this the structureless longer wavelength band. You need to confirm about, because sometimes you can have a confusion with this J aggregate and the X-imer, okay. So excitation spectroscopy, because different emission will coming from different species, so different species will have a different excitation. So the fluorescence excitation spectroscopic technique is very useful to diagnose or to detect such hexameric and dimeric species present in the medium. And as I said you earlier that these type of species are very interesting while designing various the electronic devices, especially the aggregation, the aggregation induced emission. So organic light emitting diode has application of this type of aggregation induced emission. So J aggregates, especially I'd like to mention here that J aggregates, these are the fluorescent aggregate, they can fluoresce, okay, but they are very quickly fluoresce, not like the monomer has longer lifetime. So J can but it has the fluorescence, but each type of dimers is they do not fluoresce. So when there is a large number of H dimers are forms in the medium, in general there are some exception, you can go to the literature, but normally in general the H dimers are non-fluorescent, and it can reduce the number of monomeric species in the in the medium which can emit the radiation. So there is automatically, due to the formation of the H-type dimers, there is a reduction of the emission intensity, steady state emission intensity. So this is a very fantastic I mean observation in the fluorescence measurement while dealing with the organic molecules, both in the solution or in any restricted media. Okay. So this is very interesting and a very general discussion today what I'm talking about. So, and you need to consider all these important phenomena while explaining the experimental data regarding this type of emission. Well, so another observation is that excited state. Is it okay? The next slide, Dr. Hussain?
Yes, yes.
Okay. So the another observation is the fluorescence resonance energy transfer. Okay. So it is another interesting I mean observation in the fluorescence. That has very useful applications in designing the sensors in the case of the biological for determination of the various biological species in vivo and in vitro, and also this type of energy transfer is very important while designing artificial photosynthetic system, and also to increase the various the molecular transducers, increasing the signal and the molecular transducer. Okay, the optical molecular transducer. So this is a very interesting the resonance, and the mechanism is very simple, that when the molecule is excited, there are two different type of molecules have different excited dynamics and different lifetimes. So if they are excited if they are come closer, generally 1 to 1 nanometer. So what will happen if the suppose the first molecule one acts as the acceptor, another acts as the donor. Suppose when the donor is excited, so it can transfer its excited energy via some resonant long range dipole-double interaction with the neighboring other molecule, which is the acceptor. But there are some criteria to no, any molecule cannot accept, because criteria is that the distance should be optimum, that is 1 to 10 nanometer, and also there is some overlapping between the absorption spectrum of the acceptor and the emission spectrum of the donor, which is shown in this picture. Okay, the right hand side, the top corner. So it is overlapping. So this overlapping will give you the information about whether there is a possibility of the resonance energy transfer or not. So it's a long range energy dipole-double interactions. So what will happen when both the dipole oscillates, they can interact resonantly. So as a whole, there is a enhancement of the fluorescence intensity of the acceptor. Okay, so because of the resonance as the resonance occurs. So energy transfer is based on the concept of treating excited fluorophore as oscillating dipole, and that can undergo an energy exchange with a second dipole, okay, having similar resonant frequency. So this is the criteria. So so frequency, I mean, they should be in the resonant range. Okay, so resonance happen only when there is a close the the dipole oscillations, otherwise it will not happen. Okay, so situation is very similar to the coupled oscillators, such as a pair of two tuning forks. If you vibrate with the same frequency, then you come closer, then there is a, you know, the resonance in the sounds in the school level physics. So this is the reaction scheme, that D is the donor and H is the H nu is the the incident light energy, and so it gets excited, the D get excited. So excited energy, this donor, and ultimately it will relax to the ground state, and A star is the excitation of the this is of the acceptor, and it can also relax after a certain time depending upon the nature of that particular donor acceptor material. Okay, so these are the criteria, as I already told you. The overlap integral, the extent of the area under the curve, you can have the overlap integral. Okay, so this integral is very important to determine the how much energy will be transferred to from donor to the donor to acceptor. And this is the schematic energy level diagram for the freight to occur, okay, from donor to the acceptor. Okay, you see, and this is this transfer is non-radiative. When this donor transfers its energy, there is no radiation, but radiation comes from the acceptor actually. So you will find the sequential increase with the steady state intensity of the acceptor wavelength in the emission wavelength, with increase in the donor with acceptor concentration. Okay, so this is fantastic observation in the emission fluorescence emission spectroscopy, and huge application in the biosensor, artificial transducer, optical transducer, photosynthesis, etc. So interestingly, the fluorescence lifetime of the donor molecule must be the sufficient duration to allow the freight to occur. So also the lifetime should have sufficient, otherwise the two molecules should have a sufficient time to interact. Otherwise, what will happen? Very rapidly they can quench, the donor can quench. So there is no chance to give the excited state energy to the neighboring molecule for freight to occur. So, and the efficiency is defined by the relation. You may be aware about this relation, and where RG is the first radius, and at which the half of the excitation energy of the donor is transferred to the acceptor chromophore. Therefore, the first radius is referred to as the distance at which the efficiency of the energy transfer is 50%. And in many practical purposes, while dealing with the freight for the between the organic molecules, we use this equation to find out the efficiency in percentage by into 100%. So we can have the percentage efficiency for the energy transfer. Okay, so this is the very basic approach for the freight. The excited state, another excited state event for the between the two molecules. Okay, so also I forget to mention that some charge transfer reaction may be there. Another example may be there. So in the excited state, in a particular molecule can have two different groups. One is the electron deficient, electron excess, so or maybe some conformers in the molecule which due to which there is a charge transfer between the groups in the excited state. Okay, and that is called the charge transfer reaction, and that charge transfer reaction also give you some additional band in the emission spectrum. And charge transfer band is also the very is characteristic feature of particular molecule, but it depends upon different that is solvent polarity, the pH, and the temperature, the concentration. Sometimes there are a lot of parameters are involved, the step charge transfer reactions, and ground state charge transfer may happen, but that is in the ground state spectroscopy, UV spectroscopy. We are discussing in the fluorescence spectroscopy, so excited state proton or electron transfer may happen after the photo excitation of molecule. Okay, so that is also another important and that charge transfer I've not shown here. The transfer also very selective to the different conditions. So that that type of charge transfer reaction is very interesting in application to detect various elements, various species in the medium. Okay, so it has also various huge application in biological system, in the molecular system, in the field of technology and research. Okay, so these three are very common observations in many experiments with emission spectroscopy. There is a fluorescence spectroscopy you can frequently observe or using various organic molecules. Now, I think you know that the instrumentation and working principle. This is the typical instrument of the emission spectrophotometer, and this is the principle, the working working principle, and high pressure xenon arc generally required for the steady state measurement, and the excitation monochromator is required to select the molecule, because this is the just nothing but a grating actually. Okay, high blazed grating and high quality grating, and this is this grating can select the incident wavelength for the excitation, to have selective excitation for the molecule or for the system. Okay, and this is a sample chamber. The light can go through the sample chamber, and also this is emission monochromator. You can choose the range of the emission using again the grating are there, and this is electronically motor driven device, and you can select the range of the emission. And normally the sample and the excitation that this are held a 90-degree angle. This excitation and excitation, and both the excitation and emission monochromator are held 90-degree in order to avoid some transmitted or reflected light reaching to the detector, and this will create noise in the measurement, and finally it can damage also the photomultiplier tube of the instrument. And this lens can accumulate the emitted light, and photomultiplier output of photomultiplier tube is fed to the electronics circuit, and it can convert the optical signal to the electronic signal, which can be processed with the help of the software. So this is the very simple what I have explained in very short way. That is what is the basic principle of the emission spectroscopy. But there are some refinement in the instrument for better to reduce the noise in the instrument in the final data. Okay, so different instrument, different techniques they are using to avoid the noise. I mean, signal to increase the signal to noise ratio, various additional setup may be required to use the signal to noise ratio. So this is very important. Everybody should understand what is the operation of the fluorescence spectrophotometer. So I just mentioned some of the research, just overview. I'm not going into the detail, just to give you some important results of my and some other researchers are doing in this important area. The fluorescence spectroscopy basically is an elegant choice to understand the molecular mechanism in the ultra-thin film. So this is the one important molecule. This is called 1-alkyl 2-aryl-imidazole, organized in LB film. So in Admor budget film, this molecule is organized. We can design. We have assembled this molecule in LB film, and we found that this molecule can aggregate with increase in the surface pressure. But the aggregation enhances the current actually in the when we measure the electrical signal or electrical current. And also in the case of the spectroscopic measurements, we have seen there is a huge change of the emission spectrum that is here. This is the solution spectrum and the microcrystal spectrum. Okay, so solution emission spectrum shows the emission peak at 460 nanometer. The LB film shows emission before 500 10 nanometer. Okay, so there is a shift of the emission spectrum. So this shift of the emission of the LB film corresponds to different molecular species actually, and it is due to the aggregation in the restricted geometry of the LB film. Okay, so basically I'm not shown here the detailed aggregated structure, but while you do the FM, we can find out the aggregated structure. Okay, so but this is reflected in this in this electronic fluorescence spectroscopy. Okay, so you can go through this publication and you can go through the detailed discussion of this paper. Okay, so and another work done by some other group which is published in Progress in Colloid and Polymer Science. This is very interesting, as that's why I'm interested to show you here. That is, this is a molecule. This is a cyanine derivative actually. No, this is a cyanine dye. Okay, so and in this picture you see this is the absorption spectra. This 1 and 3. This is the LB film. This molecule is organized in LB film. The 3 is the number 3 is this one, the dotted line. This is the dotted line is the benzene solution of this molecule. The dotted line, first one, the solution, and this one is this dotted is the LB film. Okay, this dotted is the absorption spectra, and the continuous, I mean, this line is called the it is the emission spectrum. Okay, that is number 2 and number 4 here in this picture, number 2. So you can see this is marked here solution and the LB. So this both in this picture you see both absorption and emission spectra show sufficient spectral shifts. It is prominent. The spectral shift is prominent and towards the longer wavelength side, and the bands are very sharp. You see this band is very sharp actually compared to those of the monomer. Okay, so this corresponds to the formation of J aggregates. J aggregates basically it has a very emission absorption both should have very sharp maximum. Okay, this is the characteristics of the J aggregates, and the KNAP has proposed some formula. This is published in Chemical Physics. The narrow band of the linear J aggregate, this is bandwidth actually. Okay, so delta omega J is called the J. Okay, and it's called the monomer, the denominator omega. So it is approximately equal to 1 by root over n, where Fw, it is the Fw is this delta delta Wj and delta Wm. These are the Fwh, full width maximum from the absorption band of the J aggregates of the monomers simply, and n is the number of coupled molecules in the aggregates. So in the aggregates, because more molecules can come together to form the aggregate, so we don't know how many number of molecules. So it is the general they have proposed this type of theory. They are related in this way. Okay, so the number of coupled, or thus the size of from this theory, the size of the aggregate can be determined. Okay, and in this paper actually these two scientists proposed a theory in 1989. Okay, it is published in Journal of Chemical Physics, and that for the dependence of the fluorescence intensity, you see in the J aggregates, the fluorescence intensity there, J aggregates also fluoresce. So we are concerned about what is the how does the intensity of the J aggregates, fluorescence intensity aggregates depend on what factor. So they have proposed some model, like some theory, that tau J by tau M, J stands for the J aggregate and M stands for the monomer, and it is approximately equal to this order of 1 by n, where tau J and tau M are the fluorescence lifetime of the J aggregates and the monomer respectively. So the lifetime of this studied cyanine dye in the LB film is shorter than in benzene solution. These features are also characteristics of J-type aggregates. Okay, so J aggregates is therefore described as a sum of the n dipoles of dipole moment oscillating in phase, where n is the number of dye molecules in the aggregates. Okay, the resulting dipole is more than an individual one. Therefore, the fluorescence lifetime of J aggregate is shorter than that. I already mentioned in my discussion earlier that it is shorter than the monomer. Okay, so and also they have shown that in LV film using the different substrate, and they have measured the lifetime that, and it is also proved that the J aggregates which is formed in the LV film, and they have seen the fluorescence lifetime. These are the substrates: gallium arsenide, quartz, silicon, the gold. But in the benzene solution, the lifetime is higher, which is 2.0 nanosecond and 0.6. Okay, but I think the correlation coefficient for the fitting is not that much good, but still this is the indication that lifetime is shorter in the LV film. Okay, so this is very interesting work, and then proposed this type of theory. That's why I wanted to show you in this lecture very good information for you, those who are working in this area. Okay, another interesting, this is Professor Hossein actually in his group. I must say, I mean, I want to emphasize this work because some new information is available there. So because I have already explained the XML and the J aggregate, okay, in my discussion earlier. So that has been beautifully, fantastically, I mean, investigated in this work, and this is the and they showed a reversible transition between the dimer, J dimer, and the eximeric emission. Okay, that's why I desired to show this type of interesting work in front of you. So it is basically a indocarbocyanine dye and mixed with stearic acid, and this dye is very long name, 1 prime diacrodecyl 1 3 prime 3 prime tetramethyl indocarbocyanine perchlorate. So it's a very big name organic molecule. So DII is the abbreviation form of this big molecule name. So you can understand how this reversible transition happened in this beautiful work. This work is published in Journal of Physical Chemistry C. So you see, this is the LV film and this is the solution. Dr. Hossein, is it visible, everybody?
Yes.
Sir, it is visible. It is visible.
Okay. I am worried about the picture actually because it is not in the full screen. Okay. So this is the normalized absorbance and the normalized fluorescence, and this is the solution absorption spectra. This one, the red one, and the blue one is the, I'm sorry, red one is the LV film and blue one is the solution here. Okay, this left hand side picture, and the right hand side, and in this right hand side picture, the normalized fluorescence, and this is the 10 layered LV film, and this film was lifted as 50 millinewton per meter, and this is inset shows the excitation spectra of this dye, of the sample dye in the solution. One is the solution and excitation was on 574, and every film, that is the J aggregate, every film that was in the 706 nanometer, this was excited because emission was monitored at 700. You see in this picture 706. So but they have tried to this using this spectroscopy fantastically to prove this type of the transition between the XMR to the dimer. And this is the pi isotherm, the surface pressure versus area per molecule isotherm, to prove how the molecular interactions, they are interfaced to form the stable monolayer for the different mole fractions of the stearic acid and the indocarbocyanine derivative used in this experiment. So different mole fraction, maybe 0.1 to 0.9. Okay, yes, 0.1 to 0.9 mole fraction they have used in this beautiful work. And this is the steady state fluorescence spectroscopy of the LV film. I am concerned, my intention is to discuss about what happened in the LV film, what happened in the organic structure, about the electronic the energy levels or the transitions, the spectral change. So that's why I want to show here the steady state fluorescence spectra of the pure sample and the mixed sample assay and the indocarbocyanine dye in the material organized in LV film. So these are the 10 layered, and the number of this number right hand side small number, I think it is very hard to visible to you. This is 0.1, 0.2, 0.3, 0.4 and so on, dot, dot, 0.9. These are the mole fractions of the indocarbocyanine material compound. So for this is observation, the pure this component shows the exameric emission at 70 when we deal with the pure component, no stearic acid. Okay, so we observe that 706 we see that 706 nanometer, and they have designated as a exameric band, and this band is structureless band, so it is very similar to exameric emission band. Okay, so and also this mixed sample, that is stearic acid, when they have mixed this indocarbocyanine with the stearic acid, the LV film shows both hexameric and dimeric aggregates. But the existence of the hexameric and dimeric, the content of the percentage of the hexameric and the dimeric the aggregates are different in different mole fractions. So this work is very interesting due to that this is controlled the monomer, I mean the hexamer to the dimer in the LV film. So there are various applications for this control where the control is required, okay, in the molecular electronic devices or in the optoelectronic devices. So and this I mean for mole fraction 0.1 only this band 706 nanometer, okay, this band is present, and absorption and fluorescence maxima are very sharp and overlapping with almost, I think you see, I go back to the previous slide, you see there is very sharp maxima, I mean absorption and emission, there is no such very shift. Okay, so this is there is no such significant shift of the absorption and the emission spectrum, so the Stokes shift is very small. Okay, so and J aggregate, it is the characteristic of J aggregate that Stokes shift should be when the band J aggregate band is observed. So when you compare with their corresponding absorption spectrum, this very less or very no Stokes shift should be there. Okay, this is the characteristic property of the J aggregates. Okay, so the absorption fluorescence maxima with the almost no shift, this is the characteristics of J aggregates. So 597 nanometer band, here 597 nanometer band is observed, you see the left hand side picture. Okay, this is the aggregated emission band. Okay, from the aggregated species, and for the mole fraction 4.4 and 0.5, no hexameric emission band is present. So this is very interesting. Okay, so only the J band, you see this is 4, the color is magenta or maybe the sky blue. Okay, so these two curve so you can have this you see there is no only J band is present, no hexameric band, that is 706 nanometer band is not present. So only two that is, it is mole fraction dependent, it is dependent. Further increase in the mole fraction of the indocarbocyanine derivative in the LV film, while preparing the LV film, you see this the hexameric band increases. So this is very interesting. And for both, when you have the mole fraction 0.9, only the hexameric band 0.9 is the last one. Okay, only the hexameric band is present. So you see there is a transition from the hexameric to the dimeric, and then dimeric to the hexameric. So it's a very interesting transition for the dimer to hexamer. Okay, and it is beautifully manifested in the excitation emission spectroscopy in this paper. Okay, and this is excitation spectra. You see there are 5 curves, excitation curve. The curve one I can show you. I just a little bit magnify this one. Okay, oh sorry. Okay, no. Okay, so curve 1, curve 2, curve 3, curve 4 and curve 5, these are the excitation spectra. So 1 and 2, here you see the blue and the green color, these two, one is the for solution and another is for LV film, but no stearic acid, no matrix, only the pure component LV film. So only the hexameric band is present. Okay, because of this very similar to the solution as excitation spectra. Okay, and very similar to the solution absorption spectra. And curve 3 and curve 4, you see for the curve 3 that red shifted, no change in shape, red shifted but no change in shape. So this is called the J aggregates. Okay, this one, the excitation spectrum for mole fraction 0.4, and curve 4 mole fraction 0.8, which is and the curve 4 for the mole fraction 0.8, it is very similar to curve 1. So very interesting again. So, and only excimeric band is present, because as it is for the excimer, so it is similar to this one, so it definitely should be the excimeric emission. So curve 5 similar to curve 3. So you can compare these excitation spectroscopy results to this pure component. So you can conclude about the when the J aggregates are formed and when the excimeric bands are formed, and what is the range of the mole fraction and their transition, their between them. Okay, so this is the schematic presentation, and they have nicely presented depending on different mole fraction in this one for the different mole fraction. Okay, so mole fraction 0.2, 0.4, 0.8, 0.9. Okay, so this is already I have explained in this last slide, and this is a schematic presentation of the dimer and the excimeric emission. Okay, J dimer is basically the end-to-end stacking. Okay, but they have slightly tilted this image, but further study may be possible to find out the inclination, whether the twisted J dimer or the end-to-end, just plain end-to-end stacking, head-to-tail stacking. So this will be another study, okay, for this. So this is a very good work, a very interesting work. Okay, so up to this two examples, I have tried to explain the aggregation, the transitions using the beautiful this nice this fluorescence emission spectroscopy. Okay, now I come to the part B, that is the electrical characterizations of the organized molecular film deposited onto the solid substrate. Okay, nowadays it is very promising, as I said in the introduction, and what I have already explained, that is the molecular orbitals, the excitonic band, the HOMO and LUMO, their electronic structure in the molecule, the difference between the inorganic and organic, and the the atomic and the molecular difference of the electronic environment or electronic structure. Those are very relevant while discussing about the electrical properties of the organic molecules when organized in Lamut-Blodgett films or any other restricted geometries. Okay, so in the very basic discussion for this electrical characterizations, and finally I will give you only one and two examples where the applications of the electrical characterizations, how this is very useful to design various electronic devices. I can explain later. Okay, so in the introduction I say that the current voltage characteristics of an active component embedded in between two electrodes can be utilized to estimate the material properties such as conductivity, charge carrier, mobility, and charge injection efficiency. During the last several years, various types of electronic and optoelectronic devices based on organic and polymeric materials, including organic light emitting diodes, organic field effect transistors, organic photovoltaic cells, organic memory devices, etc., by knowing the IV characteristics under different conditions. And various highly conjugated molecules, organic molecules especially, I'm talking about, the organized in restricted geometries such as Lamut-Blodgett films, so excellent optical properties, electrical properties, which are suitable for fabrication of various molecular electronic devices. In contrast to the inorganic compounds, conjugated organic compounds have better stability, low oxidation, low cost synthesis, wide variety of available compounds make the area organic electronics is a promising for device application in with better efficiency. So, and till date, the microelectronics industry still most of the electronics industries are concerned with silicon based inorganic, but it has started to the organic electronics as emerging emerging technology revolution. It is their technology for the next generation electronic devices. So it is emerging, it is evolving in very rapidly. Various scientists around the globe is working in this important area, which can revolutionize the electronic industry, which can revolutionize the size of the devices, the size of the substrate, the flexibility, the many interesting thing the organic molecules can impart, and which can finally which can improve our consumer life. So whenever talk about the organic electronics, the organic electron device which in which the semiconductor is basically an organic material. In organic electronics, the semiconductor which is used is basically the organic material, and even insulator which is used in some organic devices, which is also the organic material. So, and this one layer of organic material must be there while talking about organic devices. And we must say these three legend, that is Alan G. McDermott, Hideki Shirakawa, and Alan Higer. These probably all of them from the United States, and one from Japan, Hideki Shirakawa. So they invented the polyacetylene, which is the conducting polymer, in 1977, and they discovered that the conductivity of the polymers can be increased sufficiently with improved electrical performance for various device application. And for this revolutionary discovery, they got the Nobel Prize in Chemistry in the year 2000. Okay, so that is the first inspiration for the organic electronics, and then it is still emerging in a very rapidly. So where is the interest with the organic molecules for the next generation electronic devices? So we first very basic things we need to emphasize in this lecture, that is the different organic, what is the difference between, this should be difference. The difference between inorganic and organic semiconducting compounds. First of all, the inorganic compound, the bonding. Inorganic semiconductor has the bonding type covalent and coordinate, like silicon, germanium. And organic, the atoms are covalently bound, but the molecules are held together by some van der Waals type of interactions. So that's why the molecules in organic systems are much more flexible than the inorganic material. Okay, and also the electronic structure, electronic behavior is also different. I will come to that discussion. The main entity, okay, the organic electronics processing of the materials is very low cost compared to the inorganic semiconductor, and low cost substrates of any type like plastic, paper, or even cloth can be used as the substrate for manufacturing the organic electronic devices in nowadays. So directly, and the organic compound, it can be directly integrated into the packages, right, into the devices, okay, or directly for the end user, and it can be so that's why it's a very lightweight and very miniature form. So organic compound directly can be integrated on the chip on board, on the circuitry directly. Okay, so it is very interesting, the property interesting advantage of the organic material. And the solution processing is possible for various spatial approach the organic molecule. So these are mostly the advantages of the organic molecule. But what is the main difference? It is the electronic structure. One has to understand about the electronic structure, why it is much different than the inorganic counterpart. And this is the band diagram, band level, energy level, that is the valence band, and this is the conduction band. You see the green, two green, the lower and upper. For the inorganic, this was the inorganic, and this is the Fermi level, and it depends, position of the Fermi depends upon the what type of doping you have used, p type or n type. And this is the organic compound, and organic compound electrons is basically we are concerned about the HOMO and LUMO, or the HOMO -1, LUMO +1, etc. Different discrete energy levels. And when the sufficient energy is absorbed by this molecule, then by the molecule, this electron can jump to the LUMO, and LUMO is the lowest energy and is the highest energy, HOMO. So HOMO, the electron can go there. Okay, so okay, this is the lowest unoccupied molecular orbital, this is highest occupied molecular orbital, this is a fully occupied, and the spins are up and down. This is the singlet state. So what are the, and as I have told you that organic semiconductor is the main component for the organic electronic devices, and for the various thin films, even in the organized structure in the Langmuir film, we are concerned about various organic semiconductor conjugated materials. So it is to understand that what is the organic semiconductor. Organic semiconductor are critical materials for a wide range of next generation electronics and energy devices, including thin film transistors, solar energy converters, thermoelectronic devices, chemical sensor, biomimetic and bioelectronic systems. But we are not concerned about a very single molecule, small molecule here. Okay, single molecule electronics is there, don't get confused about that. But in the present discussion, we are not concerned about the small molecule. Okay, because most of the cases we concerned about the complex molecular system for the real application. Okay, so we need to focus our attention on the networks of the atoms. Okay, this the right hand side picture. And so when this network is formed, how the atomic orbitals are modified, I have given some brief introduction while talking about the fluorescence spectroscopy. Here also I again emphasize this molecular orbital, how is it formed, the bonding orbital. This one is, in case of hydrogen, very simple example, hydrogen, 1s2 and 1s electron combined together. One is called this energy, and another is called the anti-bonding orbital. Okay, so this is the bonding orbital and anti-bonding orbital, and these are called the HOMO and the LUMO. And this the span of this energies increases basically when the number of atom increases. In this picture you see when this overlapping of the atomic orbitals are there, you see the number of atoms over this axis, A1, 2, 3, 4, this increases actually. Okay, so number of these levels will increase, number of the LUMO levels will also increase. Okay, so in case of single molecule, two atoms, very simple case, only you have the two in a discrete energy states. But for real complex systems, you will find out the more energy states like this. So there will be a gap between the energy difference between the HOMO and LUMO, which is responsible for the absorption, transition, and the current conduction in organic molecule. Okay, and another interesting thing, when you talk about the molecular system for both for the electronic spectroscopy as well as for the electrical characteristics. So especially for the electrical characteristics, one important term is called the delocalization. So delocalization is very important term, important condition has to be achieved by the molecule, and delocalization is an important event within the molecule in order to spread the electronic charge to spread out to more area, so that the molecule becomes stable and resonance occurs. Okay, so you know the Lewis structure, the dot, in our school level chemistry, that dotted the electron pair and the lines are bonded, covalent bonds. So in order to maintain that structure, so or the resonance I'm talking about, the resonance, the delocalization is called the spread of the electronic charge. I mean, the electron here we must say about the molecular orbital electrons, that is sigma, pi, etc. Okay, so these pi, sigma orbital electrons can mostly the pi orbitals, they can easily delocalized through the bonds, okay, from one atom to another atom, then another atom. So this means that electrons are not confined with one or two atoms. So electronic wave function basically is distributed over the so many atoms, so you will get electron cloud actually. Okay, so more the delocalized electrons, more will be the current flowing through the molecule. Okay, so the more precisely it is the distribution of the electron density beyond the fixed place, such as a single atom, lone pair. If you have a lone pair, some nitrogen, oxygen is lone, sometimes lone pair, many molecular system, so same thing will be there. Okay, so via resonance, and resonance is a method of describing the delocalized. So resonance happens through the delocalization. So resonance is a method of delocalizing describing the delocalized electrons in some molecules where the bonding cannot be explicitly expressed in a single Lewis structure. So single Lewis structure is not sufficient to explain such type of complex resonance structure. Okay, that delocalization is very important to explain the resonance in the molecular system. So one has to understand this important molecular phenomena, because to choose the molecule, more the number of delocalized pi electrons present in the molecular system, more will be the current conduction provided proper. Another important thing is proper conjugation. So the proper conjugation of the electrons should be there through alternate single and double bond. So there should not be any interruption. Okay, so more alternation, single and double bond in the structure, so more conjugation will be there, more electron pi electrons will be there. So and if the if the LUMO level receives some more electrons in a process, then conjugation may also be extended, resulting increase in current through the molecule due to decreased homo-LUMO gap. Why this is happening? In case of the organic molecules, when you talk about the metal organic interface, many times you say you will see in the paper that that the electrons from the metal electrode can be injected to the LUMO level. Okay, and so this process is to be continued, and as a result, the electrons can be conjugated and the pi electron conjugation will be extended to the another molecule. Okay, and so on. So in case of the molecule, when talk about the molecular electronics, the conduction is from molecule to molecule. Okay, but in atomic electron, or in the inorganic periodic crystals, the electrons basically in the valence band or conduction band, the electrons is free and free to move throughout the crystal. Okay, so it's there is no some restriction of that. So here the hooping type of conductions may happen. Okay, sometime tunnel type of conduction is there, but it depends upon the different circumstance, different condition. So molecule to molecule, the molecule to molecule conduction is there in case of the organic molecular electronics. Okay, so more conjugation, more extended pi system, more extended pi conjugation, more electron will lead to the more electrons, more current flowing through the circuit. Okay, the external circuit. Okay, and more will be charge collected at the electrode ends of the organic, both ends of the organic molecules, organic layers. Okay, here I see the ethane molecule because maybe to give you a more easier explanation, that is the ethane C2H4, and you see these two the p orbital, this loop. Okay, the similar loop, this can in phase overlapping wave function, and this is out of phase overlapping. So you see that the bonding orbital is there. In case of the bonding orbital, that is called pi orbital, because the p orbital overlaps, it's the pi orbital, it is extended. You see in this picture here, this p orbital pi orbital is extended in a single molecule. Okay, I am talking about a single molecule, and this can extend more and more molecular system. Okay, so and if you see the upper picture, you see that this is less stable because out of phase overlapping the similar loop. Okay, so it is called anti-bonding orbital. I have several times I have mentioned this thing. So this is the mechanism, and this is less stable. Okay, and this is generally a pi star. So pi less stable. So pi star electron when go to this energy state, it is less stable. Okay, so different how the different conductivities come. Okay, what is the explanation behind this? So conductor, so this is the conductor, no band gap. This insulator, some band gap will be there. And for the semiconductor, if you talk about the organic semiconductor, some band gap will be there for the HOMO and LUMO level. Okay, because the bonding orbital and anti-bonding orbital is there. So you can imagine, you can compare with the valence band, the bonding and conduction and the anti-bonding orbital, although it is different than the inorganic valence and conduction band, because these are the discrete levels. So the band gap, so when this energy band decreases due to the conjugation, and when this LUMO level, this is received much more injected with the electrons, so the gap will be reduced. So it can continue to flow the electrons, and the electrons can be collected at the ends of the electrode, of the ends, that is that at the interface of the metal, the electrode, and the organic material interface. Okay, so this is the Fermi level of the material, and this is the field states. I mean, field states means the HOMO is the empty state, the lowest unoccupied molecular orbitals, and this is the energy gap. So the most interesting feature of the organic molecules is that they can easily bend their bonds. As I already told you, the flexibility, so resulting the change in the overlap between the different orbitals. So how the overlapping contributes to the different degree of the current flowing through the circuit due to the different orbital overlapping. So as the organic molecule is very easy to bend because of flexibility of the molecular bonds, generally pi orbitals are most responsible for most of the current conduction through the organic molecule. So the extent of overlapping of the pi orbitals may determine the overall resistance of the material. So more overlapping, so more current will be flowing. When the two benzene rings are in the same, as for example, if you talk about two benzene rings are in the same plane, there is a possibility of maximum overlapping. But when out of plane, so the pi electron is less possibility of the the benzene, the pi orbital. So less current may be there, the high resistivity. So the resistivity, conductivity is manifested using the manifestation of the orbitals in the organic and their overlapping in organic semiconductor or organic molecules. So while dealing with organic electronic devices, these are very important aspects one has to understand. One has to keep in mind to choose the important conjugated materials, and you can understand, you can anticipate what will be the current, what will be the resistivity using this preliminary concept. Okay, so the flexibility of the organic molecules is the most advantageous for modulating the current conduction. So that's why the flex is important. So Langmuir-Blodgett technique utilizes the flexibility of the molecular system. So when you compress the molecular system, so due to the flexibility of the molecule, we can orient the molecule in a desired form. We can orient the dipole in any desired directions. We can reorient the centrosymmetric arrangement to the non-centrosymmetric arrangement of the dipoles. So different things you can manipulate using the Langmuir-Blodgett technique, ultra thin structures. So keeping in mind all these basic concepts, you can manipulate these molecular systems to have the optimum performance of the electronic devices. And the comparison of the organic semiconductor with the inorganic, these are written here: charge carrier, polarization, charge transport, carrier mobility, exciton. Okay, one thing is important: exciton is a Frenkel type of exciton where the electron and hole normally in the organic molecules, electron or holes not separated, when light is irradiate fall on the organic material, electrons excited, and when electron try to relocate or try to the displace, some holes are generated, but normally it is very difficult to dissociate the electrons and holes in the from the organic crystals or organic systems. And so charge separation from the organic system is very difficult, so resistivity is very high. But in case of the inorganic is called one-year Mott type of excitons. Excitons are generally neutral in nature. The whole electrons combinedly you can talk about the excitons. So there are different type of excitons are there in case of different type of materials, the Frankel and one-year Mott type of excitons. You can go through the detail about the theory, exciton theory. Okay, so most of the organic electronic devices are fabricated from thin or molecular assemblies onto solid substrate due to the unique surface and interfacial properties, during optical properties, unique dipole moments, better electron conjugation, etc. So the Langmuir-Blodgett technique is important to manipulate, as I explained. I'll not go to the detail. I hope you are already familiar maybe this technique, and there are some lecture also on this important technique, how to deposit Langmuir-Blodgett thin film. So I'll skip this point. Okay, and experimental techniques for electrical characterization of organic thin film onto the solid substrate. So there are various important aspects, important things keep into our mind, to keep in our mind while before performing the organic electronic experiment. The substrates is very interesting. Commercially available indium tin oxide substrates are very commonly used, and so, but well, organic and ITO is advantageous and is highly transparent and is suitable for various optoelectronic application. Am I audible and visible, everybody?
Yes, sir. Audible.
Okay,
Audible.
okay.
Visible.
Okay, so ITO substrates is used electrodes for photovoltaic and solar cells. So, but ITO has some some problems because it has high roughness. It has the temperature is not so temperature friendly, because the resistivity can increase with the temperature, because those who are try to work with high temperature, the resistivity can change, so it can reduce the performance of the device. So that's why ITO is okay, but for particular purposes. Okay, so and another type of why I've not written here now. Okay, I can tell you the FTO, which is called fluorine doped tin oxide, FTO, which is also very popular because it is temperature friendly. Up to 600 degrees centigrade, this type of substrate can tolerate it, and without any significant change in the resistivity, and much transparent to the visible light, this FTO. So, oh yeah, it is written here. Okay, I don't see here. Sorry. Fluorine doped tin oxide is also I have shown in my slide. Okay, so it is also very interesting. Okay, and resistivity does not change up to 600 degrees centigrade, much more significantly. So it's very interesting. And those who are trying to work on the more transparency of the substrate, they can use FTO. So polyethylene, and nowadays the electronics is basically the wearable electronics, the flexible electronics. You can wear the electronic device, you can bend the electronic device. So you see in the picture, the printed flexible organic electronics is a clearly growing opportunity in the next generation electronic devices. Okay, a more flexible electronic device will come in the coming days. And polyethylene terephthalate is the well-known flexible plastic substrate for various optoelectronic applications. And another important thing is to understand the fabrication of electrical contacts. It is another interesting thing. How do you make the contact or electrical contact? Okay, various metals like copper, gold, aluminium, calcium. Okay, this can be used to or silver. Okay, silver also can be used to make electrical contact, and high quality gold, aluminum by this contact may be deposited in different way by thermal evaporation and the sputtering technique or any other technique. And but choosing this contact this metal is very important, keeping in mind the homo-lumo difference of the intended desired working material, organic material, and the work function of the electrode is very important to compare their energy level. So it is very, when you talk about the electron injection, so it is very important to first measure the LUMO energy difference between the work function of the metal and the LUMO to estimate to anticipate what will be the best metal electrode for your work. Okay, so very interesting. So and this is important point for to while experimentally do the molecular electronic devices. So low work function metals such as aluminum, magnesium, calcium, while expected to have lower electron injection barriers. So lower electron injection barriers, and that means the barrier height will be low. Okay, this type of metals, the barrier height due to the metal organic interface. Okay, there is a potential barrier. Okay, if large barriers, it will be difficult to cross the electron to inject to the LUMO level. And also some of the metals may oxidize very easily, so we should avoid those things, the oxidation or possibility of oxidation of the electrodes. It can sufficiently reduce the performance of the device. These are the work function of some metal. So metal organic interface is height, barrier height, and it can simply calculate by the different ionization potential, electron affinity, work function, difference between work function and ionization potential for p type, and work function and the electron affinity for n type. So these are very important to consider while choosing the different metals for the electrode. And another thing I must mention, I think 15 minutes have, okay. I think okay, so that is the band bending, which is very interesting. When you make a contact, electrical contact, and make a contact, metal contact with the organic material layer or surface of the organic material, so the electron acceptors receive charge from the semiconductor until their acceptor levels are energetically in resonance with the Fermi energy. So the resulting ground state charge transfer across the interface gives rise to the formation of space charge accumulation region, and this is the space charge accumulation in that region. There will be a slight change in the energy distribution in the ground state of this organic material. So that is why there is slight bending of the band of the valence band or conduction band of the material, or the the HOMO and the LUMO level. Okay, you can say the HOMO and LUMO level. Okay, so this picture explains how this band is bending, and so this is the Fermi level. Okay, so this is while you talk about the interface, this is very interesting consideration, important aspect for the molecular organic electronics. Common method, I will not go to the details. Some you may be aware of this technique, thermal evaporation technique. Just thermally target sample is there, copper, aluminum, whatever, and it can be heated by a filament, and it can go after evaporation. It can go towards the sample is mounted here at the top, and important thing is that the mean free path of the molecule of the target is about 1 meter. So if you place this substrate below the 1 meter, so most of the molecule will reach the target substrate in a straight line. So you will have a homogeneous film growth of the metal on the substrate surface. But high vacuum is required because this metal can be oxidized. So vacuum maybe 10 to minus 5 torr is okay. Soft aluminum or copper, this type of metal. Okay, but gold is not possible because high temperature is required. And another is a sputtering technique. I think you know this technique. some argon gas is injected inside the chamber, and that gas is ionizes. So, and the subsample is here and the target is here. When some high voltage is applied over this and this, so the sample target molecules can target atoms can come in different directions, and during the collision with the ionization, for the collision with the argon gas, it can ionize and it can create positive ions, and you will see some visible light inside the sputtering chamber. Okay, and you can wide area of the substrate can be homogeneously coated with the help of sputtering. Okay, so you can go through the literature for better, more detailed discussion about the sputtering and technique. And this is the connection diagram. The two probe is used, and top is a, for example, if you can gold coat on the top surface of the LB film, and bottom surface it is the ITO. So one connection from the ITO and another is from LB film, and this is connected with a high precision source measure unit. And for optoelectronic application for such a solar cell, this simply you can irradiate this sample with the light, and you can measure the current. And for temperature dependent studies of the IV characteristics, you can put the sample directly in a oven, and very highly controlled oven, and you can incrementally change the temperature and you can measure the IV characteristics. So it's the experimental procedure. Okay, what I have explained. Now some applications I try to just overview very fast. Some application of the electrical characteristics. This is the what I did. That is the same what I have shown, the 1-alkyl 2-aryl as a imidazole. This is a conjugated molecule, and this is the LB compatible material because long chains are there, and is optimized geometric structure by density functional theory, and homolumo gap is found to be 3.52, and this is 60 layer LB film is deposited on the substrate, and we found this type of Schottky behavior, and the DC conductivity has been calculated. The barrier height, what I have explained in the barrier height, the barrier potential, all these are explained, and also this homolumo is correlated with this conduction, current conduction, and also the ideality factor also defined. So this is the diode has been fabricated with the help of this technique. Okay. So DC current voltage characteristic of the LB film device get perfectly nonlinear, rectifying behavior, one unidirectional, and tested bias voltage -1 to +1. We have tested. This is the organization of the LB film. You see the aggregated structure here. So in general, the electron-rich conjugated structures of the imidazole facilitate versatile non-covalent interactions such as hydrogen bond or pipette stacking interactions. So due to the pipette stacking interactions and the compression in the LB film, the interaction also increases and it induces the aggregation of the molecules. And due to that reason, there is a the more conjugation is highly increased and current is also increased. Okay, so this is the and pipette interaction is of the aromatic ring structure under the barrier compression. It enhances the more pipette interactions. It induces. So another is the resistive switching of you have some collaborative work with Professor Hussain. So resistive switching of the tetraindolil derivative of ultra-thin films. Here we have designed a potential candidate. It is the candidate for non-volatile memory applications. Okay, so this is the molecular structure, and we saw that the bipolar switching is observed from the bias dependent. The change in the bias, we have the bipolar, one minus to plus bias or plus to minus bias. The off or on state basically changes. Okay, the molecular name is 1,4-B indolil 3L. This is a very big name. Okay, 3-methyl benzene indolil 1. This is the derivative of the indolil tetraindolil derivative. So 60 layer everything was deposited, and this is the memory devices. IV measurement was done, have been performed, and on this you see the minus 2.45. The current increased abruptly, and when minus plus bias to minus 2.45, the current abruptly increased and it is called on state. So on state, that is from high resistive state to the low resistive state. Okay, so it is the on state. So memory requires the different state, resistive memory, so on or off state. Okay, and also the retention of the on and off state after withdrawal of the bias potential. So when the scanning voltage is reversed, minus 2 plus, the device switches back to the high resistive state when the scanning voltage is reached about this. Okay, at this point the device was reset because 1 to off state, so it is reset. So you can consider the first one, the off state, on state is the set operation, and the reset is the writing. The writing operation, and is the erasing operation, reset. Okay, so this is estimate. This is the change in the current with the bias. Okay, and basically what happened internally, the molecule, the oxidation and reduction happen with the change in the bias. So bias dependent oxidation reduction, and then in an electric field, the driven conduction mechanism was the key factor behind this of switching. Okay, so IB characteristics revealed that LV film switching devices had a higher memory window than this. We have also spin coated film. I have compared. I have not shown here, and that data retention is very high, 5400 seconds. Okay, and this paper is published in Langmore. Okay, so very fun, interesting work, and we can have the idea about the on-off state for the and how this. My intention is to here in this presentation how the on and off state is correlated with the of the oxidation change and the reaction change. That is the how the molecular how the electronic changes actually what happens inside the molecule. So oxidation change, electronic states also changes. Okay, so it is highly correlated with that one. Okay, so I hope this is okay. And there are many other applications for the IB characteristics. You can have organic light emitting diode, organic thin film transistors. These are the schematic of the operation. In the organic light emitting diode, hole and electrons, the recombination rate, it is required to have large recombination. Okay, before going to the ground state. So recombination, increasing the recombination whole electron, it is a challenge in the organic material, but it is still there are a lot of results published, a lot of devices already fabricated for light emitting diodes from the organic materials for the recombination of the electron holes. This is the thin film transistor. So you can go through many other applications, the sensor, transducer, piezo properties, pyrotic properties. Okay, there. So organized molecular assemblies, LV film have many wide applications in the. So it may be the promising technology for the coming generation electronic devices. And in conclusion, what I say that fluorescence spectroscopy is a powerful approach to understand various excited state properties and their radiative relaxation for wide variety of organic molecules organized in the restricted geometry of Langmuir project films. The control and mechanism of aggregation of organic fluorophores in LV films can easily be determined by steady state fluorescence emission and excitation spectroscopy. Most interestingly, the change in the fluorescence signal is highly selective to various parameters such as mole fractions of the emitting components in the mixed LV film. The electronic structure in molecule is different than that of the atom. Molecular orbitals are play the role of various transition in organic molecules. The electrical characteristics such as current voltage characteristics of organized steel film deposit via IB technique offers promising applications in various organic electronic devices such as memory, Schottky device, diode, etc. The charge transport mechanism in organic molecule is complicated and depends upon several factors when compared to inorganic compounds. Organic electronics is gradually emerging as the next generation high performance molecular electronic devices. So I thank all of you for your kind patience. Thank you.
So
I take a lot
it
of
was
time.
a wonderful lecture. Thank you, sir. We have got you for after many days. So I hope participants enjoyed the lecture very much. Now I would like to request all the participants, if you have any questions, you can directly put it on the chat box, or else you can unmute yourself and ask to Professor Pal directly.
Hello, sir.
Yes.
Hi. Thank you for the great lecture, sir. I have one simple basic question. Like,
Okay.
in these organic electronic devices, we use said the conduction is hopping and the mobility is around a maximum of 1 centimeter square per volt
Yes.
second. But
Yes.
if you think of inorganic, it shoots up to hundreds. So
Yes.
in that case, those inorganic devices would be faster when compared to organic. And can you please comment or discuss something
Yes.
more about how mobility is like a down factor for
Yes,
these?
yes. It's a very good issue, a very good questions what sir has raised. The resistivity is very much higher actually compared to the inorganic, the conventional inorganic semiconductors like silicon, germanium. But what happens? The flexibility is important, but and the the applied bias potential, the loss of the potential is also important in this case of organic electronics. And the size of the devices is very miniature form. And although current is smaller than the inorganic compound, but I like to mention for all of you that the nowadays scientists are trying to think about the molecular wear actually, which has the conductivity like the inorganic compound, like a very high the wear, the inorganic wear. Okay, that means the molecules can be arranged or stacked in between two electrodes, and the molecules will be fabricated or synthesized in such a way so that there will be a high delocalization, high conjugation is there, so that there is a continuum, there is no gap in the the homo-lumo, so that electrons can easily collected in the two ends. Okay, so this is still in the early stage of research, the molecular wear. That's like a wear actually. So molecule can act as a molecular, as a wear, just like the copper wire and gold wire, something like similar to that. Okay, but still it is very early stage of research. And but the most interesting is that we can compromise on the conductivity on the electronic organic molecule, but the selectivity, the responsivity, the loss, the bias selections, the size, the flexibility, data retention, all these are very interesting other factors also, which should keep in our mind to go to the organic electronics. And also the selectivity, because the organic light emitting diode, organic light emitting displays, more the more selective colors you can get from the organic system. Okay, so the question is very pertinent in this discussion, but still there are some challenge on this to increase the conductivity of the organic molecules. The graphene, some of the materials, thiophene, some pyrrole, there are many materials, they are conducting polymers. People are trying to do that. Thank you, sir.
Thanks a lot, sir.
So I hope it clears the doubt of Mr. Laxman. So next I can see there are two questions in the chat box. Sir, shall I read it for you?
Yeah.
Okay, I'm reading, sir. I'm reading. No issue.
Okay.
Sir, if the memory device has the writing and erasing property, what may be its use, as you have mentioned in case of indole derivative?
Okay, very good question. So if the memory device has the writing and erasing property, what may be used? Okay. No, we actually have tried to understand these writing and erasing property, just considering the because in the memory, in the random access memory, okay, it is the resistive random access memory, as I mentioned, and this I mean and it is the non-volatile approach, because after the withdrawal of the electrical bias, they're still on the same phase. Okay, so it can be used in the random access memory, but more refinement may be required for optimal performance, but it is it's showing such important implication for the it already shown that memory memory properties, because on memory, generally memory basically what happens, it toggle between on and off state. Okay, so it shows this type of property. Okay, but for the real practical applications, maybe some refinement may be required. Okay, thank you. Other questions? Thank you so much for this question.
Yes, sir. Yes, sir. There are other questions. If the electron is already in excited state, and if we provide more energy to the electron, what will happen about that electron?
Okay. If the electron is already in the excited state, actually excited state is not the normally favorable. Okay, normally if there is no excitation is there, but what happens, excited electron in the excited state, it can relax to the different vibrational levels. It cannot stay in the excited. It can share, either it can non-radiatively it can transfer to the other molecule, other chromophore, nearby chromophore, if the dipole resonance occur, or it can it can what happen, it can intersist, it can cross, it can flip the electronic spin to higher energy, higher multiplicity state. Something may happen.
Okay, I think that clears the doubt of Dr. Nana. So next, as I can see, Mr. Lakshman is asking for PPT. So I think Professor Pal, if you send the PPT to Professor Hussain, then he will be sharing it into.
Oh, sure. Thank you. No problem.
So as I don't see any other question, participants, if you have any more questions, you can directly unmute yourself and directly ask to Professor Pal. As we can have little bit more time. So I guess there are no more questions. So now I'm handing over to Professor Hussain for the later part. Thank you.
Thank you, Ritanova. So I thank Professor Paul for delivering the lecture. So it was very informative with lot of exciting references. So I hope the participants enjoyed and also benefited from his lecture. So on behalf of the Department of Physics, Tripura University, and as a head of the department, also as a coordinator of the program, I thank Professor Pal for delivering the lecture, and I hope Professor Pal will share his PPT, and I will share it with all the participants. So there will be Professor Pal's email and contact details. So if somebody interested can communicate it with Professor Pal in later time. And dear participants, so today we are in the 5th day of the program, and tomorrow there will be last lecture for this online week. So I request all the participants to join tomorrow by 7 o'clock. Please follow the time, and hope you will enjoy. And tomorrow, Professor Devajyoti Bhattacharjee, he will be lecturing. With this, we are going to end these sessions. Thank you very much for joining with us. Good night, and hope to see you tomorrow evening. Thank you very much.
Thank you all. Okay. Dr. Hussain?
Yes.
Okay. So So it is end. Okay. So we can talk later. Okay.